Tes. Okay. Okay, thank you, MC, very much. Thank you very much for the introduction. Okay, good afternoon, everyone, for all of you on-site and online participants. Okay, I hope everyone is still excited today to be in this lecture, okay, to be in this class. Okay, for online participants, can you hear my voice? Hello, and online participants, can you hear my voice?
Yes, we can.
Okay, I assume that you all can hear my voice, okay? Okay, as introduced before, my name is Inasanti Pandanwangi, and you can call me Inas, and I am going to be the moderator of this session. And I am a lecturer in the Food and Agriculture Product Technology, Universitas Gadjah Mada. Okay, without further ado, I would like to introduce our speaker. Our speaker for this session is Dr. Kota Shimomoto from the Institute of Agriculture Machinery, National Agriculture and Food Research Organization in Japan. And he will join us online. Okay, allow me to read his CV. So he is a researcher in the Institute of Agriculture Machinery, National Agriculture and Food Research Organization, or NARO, Japan. And he completed his PhD in the United Graduate School of Agricultural Science, Ehime University, Japan, with thesis titled Development of Photosynthesis and Transpiration Monitoring System Installable in Greenhouse. His research interests include greenhouse horticulture, monitoring system, machine learning, yield prediction, rail-guided vehicle, and maternity classification. And he also has research experiences and publications related to this topic, including the predicting sweet pepper yield based on fruit counts at multiple ripeness stage monitored by an AI-based system mounted on a pipe rail trolley, development of an AI-based fruit monitoring system with a focused illumination unit for tomatoes grown in greenhouse horticulture, and also development of double camera AI system for efficient monitoring of paprika fruits. Okay, I would like to welcome Dr. Shimomoto. Dr. Shimomoto, good afternoon. How are you?
Good afternoon. Can you hear me?
Yes, we can hear you quite clearly.
Okay, thank you. And I will share my presentation.
Sorry, doctor, can you please increase your volume?
Sorry, can you hear me?
Yeah, okay.
Okay.
It's good enough.
Voice. Yeah, okay,
Okay.
thank you.
Okay, so doctor, thank you for joining us in this afternoon. I'm very glad that you can join us online today. So, Dr. Shimomoto will give us lecture about the application, artificial intelligence application in Japanese agriculture. Okay, the presentation will run about 70 minutes, and after that, following that, the discussion will run about 35 minutes. Okay, without further ado, to Dr. Shimomoto, you may start the presentation.
Okay, thank you for introduction, and thank you very much for inviting me today. I'm delighted to have this opportunity, and so I will be speaking on the topic of artificial intelligence application in Japanese agriculture. So now I'm working for Institute of Agricultural Machinery, NARO. Therefore, today I would like to mainly introduce some of the AI application being developed in our organization. Okay. Firstly, let me introduce myself. So my name is Kota Shimomoto, and he is my son. Recently, I enjoy doing everything with him. And I got the doctoral degree in 2018. I started my research career with photosynthesis measurement. After getting a job, I was assigned in the laboratory for safety system for agriculture. I analyzed the motion of tractors roll over with motion capture cameras. Now I'm working on AI-based fruit monitoring system, which I will introduce later on. As you can see, my background was not related to AI, but I have recently started studying it, and I am now applying it to my research. This is overview of my presentation. First, I will briefly introduce our organization. Next, I will provide some background on current stage of Japanese agriculture, as well as the research context related to my area of expertise, greenhouse horticulture. After that, I will present the fruit monitoring system I am developing using AI. I will also introduce other AI applications being developed by members of our laboratory. Finally, I would like to share a few additional case studies, including those outside of the greenhouse horticulture. In this presentation, rather than focusing on the detailed structure or theoretical aspects of AI algorithm, I hope to showcase as many practical applications as possible. The AI use this example is mostly based on fundamental techniques, and the focus will be on the robot and the automation system developed using AI. There may be many technical terms, but it's not necessary to understand all of them. I hope this presentation will be helpful and inspiring for your research and studies. First, I would like to introduce our organization. Now I am working for NARO. NARO stands for National Agriculture and Food Research Organization. Our organization is the biggest agriculture research organization in Japan. And many of research institutes and research centers containing in NARO have a history of more than 100 years. The number of NARO researchers is approximately 700. Annual budget is $507 million, and we are under the supervision of Ministry of Agriculture, Forestry, and Fisheries, MAF. NARO has 21 research institutes and funding agency. So we have institutes for various fields such as agri-food business innovation, fruit tree and tea science, livestock and grassland science, animal health, agrobiology science, crop science, agro-environmental sciences, and so on. Our organization is actively working on international collaborations. So far, we have signed 35 memoranda of understanding, MOUs, with other countries and international organizations. Additionally, we have established a European branch at Wageningen University and Switzerland. Also, let me introduce our institute, Institute of Agricultural Machinery NARO. We call our organization, we call our institute IAM. Literally, IAM is a research center for agricultural machinery. So our institute was established in 1962 and started in inspection and R&D of agricultural machinery. In 2003, IAM was integrated into the present NARO. Number of IAM's researchers is approximately 70. So I am one of them. So IAM has 3 research divisions. I belong to Division of Intelligent Agriculture Machinery Research in Tsukuba. city, and IM has also 3 departments for safety tests, research promotion, and research collaboration. Our activities are consisted by 3 pillars. First, R&D on agricultural robots and other machinery. Second, safety research on agricultural machinery and farm safety. Third, international standardization of agricultural machinery. Returning to overall topic of NARO, let me introduce the research environment related to AI at NARO. Now, NARO is putting a lot of effort into research with AI. As you know, recently AI has been in the spotlight. For example, object detection with deep learning recognize automatically the location of a specific object within the image. In May 2020, we started operation of the AI supercomputer, SHIHO, and NARO-linked database. So SHIHO is the main force of the AI research. This supercomputer has 128 GPUs, and it demonstrates its exceptional performance. NARO is also focusing on education in AI and ICT literacy to train researchers in AI and ICT literacy, and to promote AI research. The Research Center for Agricultural Information Technology was established in 2020, and many experts were hired out from outside. This research center, as of the March 2021, the center's research staff members are 52, consisting of 40 AI specialists and 38 agricultural technology researchers who are pursuing 41 research themes. This center provides 4 levels AI course matched to the participant level. So NARO aims to cultivate research with AI-oriented ICT literacy, and plan to expand this talent pool to around 4,400 by 2023. Although the exact achievement rate is unknown, it is believed to be close to this value because annually 40 new employees receive AI and programming training from 2020. I also had this training course to study AI when I was beginner. I will introduce background of Japanese. Next, I will introduce background of Japanese agriculture. So, agriculture population in Japan has been decreasing year by year. The aging of the agricultural workforce is also progressing, with the average age of the farmers in Japan now at 68 years. Therefore, the development of automation systems that directly substitute for human labor is increasingly needed. In addition, Japanese government formulated green food system strategy in May 2021 in order to realize the coexistence of productivity improvement and sustainability of food and agriculture, forestry, and fisheries by innovation. This strategy is measured similar to the EU Farm to Fork. By promoting organic agriculture, we will reduce the use of chemical fertilizer and reduce the burden on agricultural land, leading to realization of the sustainable agriculture. From the perspective of robotics, contributions through improved productivity are also important. That's why our institute is developing several robots and automation systems to improve the productivity and reduce labor load. These are examples of our research and development: unmanned agriculture vehicle system and techniques for safety tests, such as static strength test of crops and fruit monitoring system for greenhouse horticulture. Here, the other example of our development, reading robot, human following robot, map-based variable rates fertilization, and autopilot rice transplanter. These robot systems paid a lot of attention from farmers. Next, I will introduce background of Japanese culture. Our research group is developing automation system for large-scale greenhouse like this one. These greenhouse are sometimes referred to as phenotype greenhouse. In Japan, large-scale houses are defined as those exceeding 1 hectare in size. They are covered with glass, and initial inside environment is controlled by various instruments. Some companies hire over 30 workers in large-scale greenhouse. Their sales are over $1 million per hectare per year. Therefore, they are required to manage workers efficiently and to sell their products strategically. In difference to Dutch horticultural practices, the next generation horticulture hubs were established at 10 locations nationwide as top learner models to address the challenges faced by our country's horticulture industry. Thanks to this project, the number of large-scale greenhouses has more than doubled in less than 10 years. However, even in these high-tech greenhouses, plant monitoring and automation robots haven't spread. That's the reality. Next, I will introduce a fruit monitoring system I'm working on. So in high-tech greenhouses, yield prediction contributes to efficient environmental control, worker management, price negotiation, and shipment planning. But currently, to predict crop yields, some large-scale greenhouse growers manually count the number of the fruits on some plants every week. It takes a long time, and that prediction performance is unstable. So in our previous study, we developed a tomato fruit monitoring system, which counts a number of fruits automatically with AI. The scanning device on the moving unit records a video and creates panoramic images of the plants. Moreover, this system evaluates the fruit maturity level based on the rate of coloring. Here, I'd like to take a moment to review the object detection and segmentation based on deep learning. First, deep learning refers to class of machine learning techniques that involve training multiple layer neural network through intensive computation and interactive adjustment of parameters. The object detection is task of finding what objects are in the image and where they are. And instance segmentation is semantic segmentation assign class label to every pixel in an image. So instance segmentation is a combination of object detection and semantic segmentation. It assigns the pixel level labels to objects and also separates different instances of the same class. The emergence of the object detection and segmentation techniques using deep neural networks has accelerated the momentum of image analysis in phenotyping studies. Previously, common detection methods for phenotyping and robot operation machine vision were based on color and temperature information of the fruit's surface. However, many studies applying deep learning-based detection techniques to phenotyping have begun to overwhelm previous methods. Regarding fruit counting system using object detection, several systems have been developed in several previous studies. These systems generally utilize stereo cameras to eliminate non-target fruits that appear in the background of noisy images. They use depth information from stereo cameras to filter out distant fruits. While these systems are excellent, depth information comes with challenges such as high hardware and the processing cost, as well as potential errors caused by inaccuracies in depth information, depth data. So we are taking a different approach. Our system adopts a unique LED illumination technique. This illumination technique removes the unnecessary objects in the background of images. Two lights from these light sources cross at the center and make slight dark contrast between the near side and the far side. So the far side plants are darkened. So we can focus on only front side plants. That's why we obtain the clear and the simple images for object detection. This is a comparison of the fruit detection performance between the conventional method and the new method. By new method, average precision. So average precision means object detection performance increased up to 0.95. From this case, we can see that while developing AI itself is important, it is equally crucial to create the environment where AI can perform well and to devise effective measurement method. Recently, we wrote an academic paper. In this paper, we evaluate the fruit detection performance of our system, and we confirmed the light intensity difference between with and without focus illumination unit. And also, we introduced our method for conversion process from video to images in this paper. Okay. In another of our papers, we evaluate the interoperability of tomato fruit detection models trained on the nighttime images collected in different greenhouses with different cultivation conditions. Here, interoperability refers to ability of the model trained in one environment to maintain high detection accuracy when applied to images from different environments, such as other facilities, cultivation methods, or times of day. Sorry, I forgot the proceed its slide. Sorry, and this figure shows images similarity visualized using a method called TSNE. It reveals that daytime and nighttime images have different characteristics. As a result, when a model trained on the nighttime images was used to detect fruits in daytime images, the detection accuracy decreased. In addition, it was found that models trained on data sets containing more diverse plant appearance exhibited better generalization to different environments. Furthermore, the image captured by our monitoring system had a background removed, resulting in the cleaner and less noisy input. Because of this, even when the training and test images were taken under different conditions, the similarity between them remained relatively high. As a result, the model demonstrates high interoperability in terms of detection performance. We also developed rail-guided vehicle and platform for our monitoring system. For monitoring, the RGV moves at the stable speed on the pipe rail. It has bumper sensor to detect the end of the pipe rail. We also developed the platform for shifting RGV to next pipe rail. So recently, we applied our fruits monitoring system to sweet pepper fruits. In sweet pepper cultivation, the height of fruiting position is getting higher along with growth. The height of the paprika fruiting position reaches over 4 meters in closing stage of the annual cultivation in large-scale greenhouse. So worker needed to ride a pipe rail trolley to harvest these fruits. Therefore, fruits in high position must be monitored for sweet pepper. So in our previous study, we developed the sweet pepper fruits monitoring system. The monitor fruits are located at a high position. The scanning device was attached to the pipe rail trolley. The trolley with our scanning device moves at a stable speed on the pipe rails. The plant scanning device simultaneously records the video of the both sides of the planting rows and creates panoramic images of the plant. And then the system detects and counts the fruits using object detection technique and evaluate the fruit maturity level, based on the rate of coloring. So this figure shows the process from monitoring to result sharing in the proposed system. So after shooting video with the monitoring system, we remove the tablet PCs from the scanning device and place them at the station with the cooling fan. This station was installed in the office of the greenhouse. At fixed hours, the program on the tablet PCs booted automatically and create panoramic images from videos captured by our scanning device. The panoramic images were split into 512 by 512 pixel squares. And subsequently, those images were uploaded to online storage at the fixed time. Analysis PC with the graphics card located away from the greenhouse downloads the images, analyze the number of the fruits in the squared images, evaluate the maturity level, and then analysis PC uploads again the result to the online storage, so we can share the result with the farmers. So this is the result. So using our developed system, we monitor the number of mature paprika fruits cultivated in 6 plant rows of the target 0.6 hectare cultivation area. This cultivation area has 144 planting rows. So measuring 6 rows means we took measurements at 3 locations with 2 rows at each spot. In the graph in the center, black markers refer to the changes in the average number of detected mature fruits in target 6 plant rows. White marker indicates the weekly total yield in the 0.6 hectare cultivation room. So in this study, we defined more than 1% of the colored fruits as the mature fruits. So the weekly total yield seems to trace the average number of the detected mature fruits within 1 week time lag. In the scatter chart in the right side, the y-axis is the average number of detected, x-axis is the average number of detected mature fruits. Y-axis refers to weekly total yield in the following week. The correlation coefficient between them was 0.95. This result implies that using the average number of detected mature fruits over the 6 plant rows, this result implies that using the average number of the detected mature fruits, the there is a possibility predicting the weekly total yield of the 0.6 hectare cultivation area in the following week. We recently wrote a paper on the scanning device for paprika fruits as well. In this paper, we confirmed fruit detection performance over 12 weeks, and the performance was not so high, but it is very stable. We also compared fruits count counted manually by growers, and those counted automatically by our system. So counting performance, So we excluded green immature fruits and only colored fruits were counted. We classified 3 ripeness stage. Counting performance for each ripeness stage are shown here. We found correlation across all ripeness stage. So we also we automatically counted the colored sweet pepper fruits at different ripeness stage using our AI-based camera system mounted on the trolley over 12 weeks. We then compare the average number of detected fruits each week with the total yield harvested from the entire 0.6 hectares greenhouse in following week. Furthermore, we built a simple multiple linear regression model using the average number of fruits at different ripeness stage as a predictors to estimate the total yield in the next week. So we evaluated the model's accuracy using leave one out close validation and calculate the prediction error with weighted absolute percentage error. As a result, the best prediction accuracy was achieved when using the counts of the 1 to 40% and 41 to 8% ripeness stage fruits together, resulting weight of 21%. Okay, from now on, so I'd like to introduce some of the research projects being conducted in our laboratory using presentation materials provided by my colleagues. Some of them are not directly related to my own work, but they are very interesting studies and a good example of AI application. So let me introduce them. So first, let me introduce the case of drone used inside the facility. The target of this study is strawberries. In the previous study, they confirmed that frequent measurement of young leaf shaped feature is effective for growth diagnosis of the strawberries. However, young leaves end up in the blind spot of the older leaves. Therefore, they came up with the method that uses drone airflow to spread older leaves and detect new ones. But it is difficult to develop the drones and autonomous vehicles in greenhouse due to unstable GNSS reception, tight space, and numerous obstacles. The first step, they use total station with automatic tracking function and drone equipped with 360-degree prism. This station monitors the flight coordinates and control propeller rotation speed. This is a scenario of automatic flight of drone. The drone takes off and automatically moves to crop walls. Then it flies along with the crop flow. At the end of the row, it turns around and measures the next row. This is an overhead images from the drone. It is detecting new leaves. It may appear to be flying smoothly, but in reality, there are blind spots due to the obstacles such as pillars, crop, and cultivation equipment, and securing space of monitoring equipment also poses a challenge. Therefore, they also developed the drone operation system utilizing the line tracing technique. This is a scenery of drone operation utilizing the line trace technique. This method was okay, not too bad, but it still had some issue, such as effort required to set up lines or markers. This is overhead view from drone. So taking off and moving to crop row, and yeah, this is it's turning around. So currently, they are also exploring a drone flight using visual SLAM, aiming for higher flight accuracy indoors without the need for special materials. Visual SLAM is a technology that allows the robot or drone to understand where it is and build a map of its surroundings using only camera images. It helps the system navigate in real time without GPS, so which is especially useful for indoor environment. So I would like to introduce a detail for the monitoring techniques that utilize drone downwash, which has been developed in parallel with drone flight technology for use inside greenhouses. Assuming a stable drone flight, the drone is fixed onto the cart and capture images from above while generating downwash. Detection models have been developed for each part of the strawberry. So in addition, a technique for identifying individual plants has also been developed. This enables time series observation and growth analysis become possible by comparing image of each identified plant. So this slide shows the per plant growth time series analysis in detail. This system always stores the metrics, new leaves area and second leaf area. On the day a new leaf is confirmed, a system updates the leaf ranking and overwrites the area of the third leaf. This allows the total leaf area to be automatically calculated. And so, yeah. The below side, the plant center is detected by a PTO detection. The budding date is defined as the first day, but is detected in the frame. So it means light blue circles. The fruit truss elongates during the flowering and branching. Their system can also detect buds that appear after branching. This allows the following flowering dates to be automatically calculated. Since time series analysis, like the one shown earlier, is possible, they are also developing an application for mature fruit count prediction. Next, let me introduce a case of robotic pruning of tomato. Pruning means the cutting off parts of the plant, like leaves, to help it grow better. So pruning is the second most labor-intensive task after harvesting, and robotic pruning is challenging for full automation of horticulture. So localization of the plant's main stems in greenhouse environment is important for robotic pruning and useful other tasks. They started by acquiring the point cloud from the RGBD, so sensors. So D means the depth. This data is then processed using the PointNet++ to perform the semantic segmentation, identify the main stem, leaves, cultivation bench, and other elements. So PointNet++ is a hierarchical neural network and process 3D point cloud data by capturing local structures, making it effective for tasks like model classification and segmentation. The point cloud is pre-processed with voxel down, sampling and pass-through filtering. So next, they evaluate the linearity of the clusters using the principal component analysis. So clusters with high linearity are grouped and skeletonized to form the main stem skeleton. The final step involves connecting the average points in each layer to create the continuous skeleton. This method allows them to accurately detect and visualize the main stem skeleton of tomato plants, which is essential for various agricultural applications. So this is a scene of lower leaf removal by robot. The hedge trimmer moves along with the main stem, removing the leaves. So next, I would like to share some examples of the AI applications developed outside our research group. So Yaskawa Electric is a Japanese company specialized in industrial automation, including robotics, motion control, and drive technology. This is a pruning robot for cucumber that suctions and removes cucumber leaves. So Denso Corporation is the leading global manufacturer of advanced automotive components and system. Denso has been selling this robot in the Netherlands since last year through the Dutch company. Similar to the pruning robot I introduced earlier, AI-based detection technology is also used in this type of working robot. In addition, many harvesting robots are currently being developed in Japan. So you can find these kind of robots on YouTube. So please look for later. So the development of the robotics for greenhouse horticulture is becoming increasingly active in Japan. So especially, yeah, there are many startup companies which they developed the robots for agriculture, for greenhouse horticulture. To make a breakthrough, startups companies key factors. So they have a spirit of challenge and passion and energy. The Japanese government has also begun making large investments in startup companies using substantial subsidy. Now, let's shift our focus to example of AI application in agricultural field other than greenhouse horticulture. This is an unmanned taxi driving on the public road in Los Angeles. As you can see, autonomous driving has begun to take a root in our daily life. This kind of trend toward autonomous driving is no exception in agriculture. This document outlines the guidelines for ensuring safety for agriculture machinery's automatic driving in Japan. The automation levels are categorized from 0 to 3. Level 0 refer to machinery operated by a person. Level 1 includes assistive features such as auto steering. From level 2 onward, autonomous machines are utilized and most tasks are automated. The key characteristics of level 2 is that the operator visually monitors the tractor. Level 3 involves in the operator remotely monitoring the tractor. So Japanese agricultural machinery manufacturers have already commercialized up to level 2. Currently, development and validation are underway to achieve level 3. From now on, I will talk about research conducted by different research group next to ours. This means the research was conducted by our institute, NARO. The presentation slides I will use were kindly provided by my colleagues. Of course, autonomous driving is in outdoor environment, is outside my area of expertise, but I will do my best to explain it. So their system integrates several key functions to achieve level 3 automation for agriculture vehicle in Japan. These functions include self-localization, 2D and 3D mapping, situation awareness, path planning, remote monitoring, and feedback control. The vehicle is equipped with sensors such as GNSS, 3D lidars, and cameras to capture detailed environment data. This data is processed to create accurate map and identify obstacles. The system ensures precise path tracking and can perform tasks like soil tillage with centimeter level accuracy. Additionally, it can execute emergency stop when obstacles are detected within the predefined danger area. By combining this modularized function, their system enables continuous road driving and efficient agriculture work. For level 3 automation with remote control, developing is primarily focused on field-to-field movement. When the tractor is working within the field, autonomous driving is possible as there is no need to worry much about the road wide or obstacles. However, for field-to-field movement, specific autonomous driving technologies are required for agriculture environment, such as entering an existing field and navigation in narrow off-road paths. So these challenges include the various types of roads, such as hay, gravel, grasses, and muddy surfaces. Additionally, there are various changes depending on the season, weather, and the time of day. The ambiguity of drivable and non-drivable areas also poses a significant challenge. Unlike urban environment, there are fewer static artificial objects such as buildings, lane lines, and traffic signs. Furthermore, the road condition can be poor, being uneven and being uneven. So first, they use the sensor like LiDAR and the camera to capture the spatial data of the environment. This data includes the location and the demonstration of objects and this data includes location and dimensions of the object. Next, we convert the maps. Next, they convert the 3D maps into our ortho image, which is geometrically collected aerial photographs. This allows them to measure distance and area accurately. They then extract the boundary points of the road and the field from the ortho image. These points help define, navigate areas. Finally, they create a 2D occupancy grid map from these boundary points. This map shows which areas are occupied or free, helping autonomous systems plan safe paths. So in this way, self-localization is primarily carried out using RTK GNSS and IMU as well as 3D LiDARs. So AI is used for situation awareness. Specifically, it is utilized for obstacle detection and drivable area segmentation. The tractor follows a pre-created map, but it's determined in real time whether there are obstacles and if the path is actually drivable. This is an experimental result. The vehicle moves from the garage to the field at the speed of approximately 0.95 meters per sec. So it detects a mannequin placed on the road and came to the stop. After the mannequin was removed, the vehicle resumed operation. It enters the field through the entrance, tillage and turning operation are performed within the field. The working speed is about 0.9 meter per sec, and turning the speed is about 0.8 meter per sec. The vehicle exits the field and enters the farm road. In agricultural field, the indoor environment, along with crop and weeds, swaying in the wind or hiding obstacles, creates a highly unstable environment for autonomous driving. Therefore, object detection using thermal camera and ultrasonic sensors is also being tried. Next, I would like to introduce another example. This is a light truck commonly used for transporting harvest and materials. It is characterized by its low cost and adaptability to narrow agricultural load. Like a tractor's, autonomous driving is also required for this light truck to achieve labor saving and automation in agricultural work. So this light truck is also equipped with many sensors, just like a tractor I mentioned earlier. This is a test course of the light truck driving experiment. They are conducting the test by closing off public road. The most important aspect of this test is to enable autonomous driving even in the area where GNSS signals cannot be received due to the influence of a tree. Therefore, in addition to conventional GNSS, they are developing the technology that installs marker poles in the area where GNSS signal cannot be received. These poles are detected by camera to understand the shape of the road. This is a scenery of autonomous driving of a small truck. So here is an area where GNSS signal cannot be received. So you can see many poles. This is the result of the vehicle trajectory. The purple lines represent the target path. The green lines represent the vehicle path, and the asterisk indicates the poles. The circle area is the pole area, and the result of crossing this area is shown on the right. You can see the target path and the vehicle path almost overlap, indicating that there is no significant deviation even in the area where GNSS signals cannot be received.
Sorry to interrupt you, Dr. Shimomoto, but your time is already finished.
Okay, thank you.
Okay. Yeah. Okay, now we will proceed to the Q&A session. Is that okay for you?
Okay, so my presentation.
Or are you going to finish quickly, maybe? Okay.
Okay.
Okay, I'll let you conclude your presentation first, then we'll proceed to the Q&A session.
Okay, thank you. So, okay, this is the conclusion of this presentation. AI will be important in all fields, including agriculture, but you don't have to become an AI expert just think of AI as tool and helps you work better. Learning AI is much easier now, so don't to be afraid to start. Even I began learning AI after finishing my PhD. Of course, AI is important, but tools around AI, like sensors and data system, are also very important. We need the full system, not just the AI itself. Also, generative AI is, so I couldn't explain that, but also generative AI is helping researchers work faster. It can speed up data analysis and help us learn new skills more quickly. Yeah. So thank you. I would like to wrap up my talk. Thank you for your attention. This photo was taken last year when I had the opportunity to visit Gadjah University. It was a very meaningful experience for me. And I would like to express my gratitude for this opportunity. And additionally, I would like to thank my colleagues who provided valuable materials for this presentation. Thank you all. Yeah, that's it.
Okay, thank you, Dr. Shimomoto. Please, let's give a big applause to Dr. Shimomoto. Okay, so now we will proceed to the Q&A session. For the on-site participants, if you have any question, you can just raise your hand and I'll call your name. And for the online participants, you can use the raise hand button in the Zoom, or you can type your question in the question box. Okay, for the on-site, okay, please from Mr. Ken. Okay, you can ask your question first.
It's okay. Check. Thank you for your presentation. I can learn a lot of newest trend of machine and AI technique and automatically techniques. Maybe it may come as a little bit surprise to you because I'm from Japan and my major is ecology in Yokohama National University. And yeah, I have two questions. And one is your institution like NARO, sorry, I don't know how to say, but has agreements with many countries. What positive and negative effects have you experienced from it? Like, please provide any specific examples. And second one is compared to other countries, how do you think Japanese agriculture levels and technology? Are they so developing or are they still under the undeveloped parts? It's my question. Thank you.
Okay, thank you for your question. First question, so let me repeat. So you are interested in the collaboration with other countries, so conducted by our organization. So my understanding is right.
Yes.
Okay. So we have a lot of collaboration, and yeah. So we can discuss with other countries' researchers about same challenges of the same field. So that's why we can get inspiring from them, and especially for young researchers, so discussion or communication with other countries' researchers is it's good opportunity, and I think. So I don't know negative point. So I can come up with a negative point. So okay, and so between our research organization and other countries' organization, we exchange the researcher. So yeah, that is also a good opportunity to enhance the ability of researchers. Oh, sorry. Yeah. Now I think yeah, that. So
Sorry,
so,
maybe it's hard to say. My bad saying, and I want to ask you a negative effect means it's too much cost or battle with other researcher in other seats because of background. Has it occurred or not? Yeah, it's my question.
okay. Of course. So we have maybe I would say so keeping the relationship and exchanging the research or going abroad is yeah, we have to pay a lot of money, so it costs a lot. But more than that, I believe that we can get so positive effect from the collaboration. I believe that. Okay. And so sorry. So what is the second question?
Oh, sorry. My second question is, wait. Compared to other countries, how do you think
Okay.
Japanese agriculture levels and technicals?
Okay, thank you. So it depends on of course, it depends on the field. So, for example, unmanned autonomous agricultural machinery, so like a robotic tractor or something, is well, I believe that our country has been developed, so compared with other countries. And but in greenhouse horticulture, so leading countries is Netherlands, and yeah, so yeah, I often feel our countries in our so there is a more room to improve. So compared with Netherlands or other countries. So yeah, it depends on the field, I think. So conversely, I ask. So I want to ask you, how about your country or Japan agricultural level? How do you think?
Oh, okay. Actually, in my perspective, Japanese agriculture level is so high because during this summer class, I learned a lot of AI technology, but I often see some arguments and get relationship with Japanese some industry and agriculture with Indonesian one. So maybe a lot of Japanese, yeah, in my guess, a lot of Japanese industry and agriculture institution has helped a lot of countries, I think. So that's why maybe, yeah, Japanese agriculture is so high level. Yeah, it's my opinion.
Thank you a lot. And so yes, so I think I agree with your opinion, but and so I think, in my opinion, so we can realize the automation successfully in my countries. So we can also so support other countries. And so therefore, so yeah, this is this is a good aspect. Or I'm sorry. So how to say? Yeah, but so success of our success of our countries is not for only our countries. So yeah. So sorry. Does it make sense?
Okay, Dr. Shimomoto. From Mr. Ken, is there any future questions, or maybe is it enough for you?
Yes, thank you. I can understand a lot. Thank you.
Okay, thank you. Okay, maybe next question from the on-site participants. Okay, I will start from the second row. Miss, what's your name? Miss Jul. Okay, please proceed with your question.
Check, yeah. Previously, thank you for the nice, insightful, and then I know what AI in Japan agriculture. Sensei Shimomoto. So I wanna ask about. I'm so curious regarding. I joined the summer course. I'm curious about. Is there any AI used to check the maternity or growth of plants such as cassava, potato, or plants in the soil maybe? Because if you look at the tools mentioned earlier, it doesn't seem to be used for plants that grow in the soil like that. So that's all my question. Thank you.
Okay, thank you, Miss Jul. Dr. Shimamoto, please.
Yes, thank you for your question. And yeah, other research groups try to detect the outside field crops, so like cabbage or potatoes or something, so like that with AI. So I think it is possible, and it's very useful for outside field farm field.
Miss Jul?
Yes, sir. Can you repeat? I cannot hear clearly, maybe.
Oh, okay. Should I repeat?
Yes, please. Can you repeat your answer to Miss Jul, please?
Okay, thank you. So in our organization, other research group is trying to detect or diagnosis the outside field crops with AI. So outside field crops means potatoes or cabbage or something. So I think it is possible and useful. So yeah, so yeah, so autonomous detection of those crops is very useful for outside field farm.
Yeah, thank you, Sensei, for the answer. Maybe in your group researcher still make that AI, right?
Yeah, yes.
Yeah. Maybe enough since.
Okay, thank you, Miss Jul, for the question. Okay, maybe one more question from the on-site participants. Please, please, can you mention your name and then proceed with the questions?
Okay, thank you for your opportunity. So, my question is, Can we detect the pigment in fruit with it, or we need to take another step to know the pigment in the fruit? Thank you.
So yes, so pigment, I would say, yes, it is possible, but it's not impossible directly. So we have to judge the image. So we have to judge from the color in image. So we have to compare with the pigment, exact pigment and the image. But I don't know, there is this kind of research is ongoing. So I'm sorry, I don't know. But I would say I believe it is possible indirectly.
Thank you, sir.
Okay, thank you, Miss Anesha. Yeah, for the question. Okay, sir, maybe I will read some questions from the online participants. From first is from Miss Nosa Finalia. So the question is, how can the collaboration between NARO and MFF effectively reach farmers, especially in rural areas, and support smart farming practices across a wider range of regions? Additionally, what about smart farming in outdoor cultivation, where most of the land has uneven surfaces? Is the technology still applicable in such conditions?
So too long. Yeah, it's too long with the questions. So could you simplify your question? So you have two questions. So my understanding is right. No, yeah. Okay, so maybe one question. Okay, so yes, smart farming. So using the autonomous machinery in the rural area is difficult, as I mentioned. So narrow paths, even road, uneven road. So, but so their system, so light truck and robotic tractors can judge the road condition in real time. So basically, so these vehicle can ride even in the rural area. And as I mentioned, in rural area, so GNSS is weak. So, but our organization developed the solve this problem. So pole system I introduced. So that is my answer.
Okay, thank you, Dr. Shimomoto. Maybe one or two last questions from the online participants. Next question is, okay, from Tan Yu Shen from UPM. Good afternoon, doctor. I really amazed by the technology in Japan's agriculture, since it's used a lot of robotic, IoT, and even indoor farming. How about the electrical power? All of these technologies need support by electricity, means that it will consume a huge power of electricity to maintain the operation. May I know how Japan government or farmers overcome these problems?
Okay, thank you. Yes, so especially indoor farms, so like a greenhouse horticulture or in the vertical farming, power consumption is very high, and some countries, so power consumption, so power cost of the power for agriculture reduced on purpose for supporting the farmers. But now, currently, Japanese government don't do that. And so, as you pointing out, electric power consumption is needed to be considered in near future. So if we promote the advanced agriculture.
Okay, thank you, Doctor, for the answer. Okay, maybe last question from the online participant from Mumtaz Hatta. Okay, good afternoon, Doctor. Your presentation is interesting for me. I would like to ask a question regarding the application of AI in agriculture. In my opinion, the data annotation process is one of the most challenging parts of such applications. How do you address or manage that challenge? I ask this based on my personal experience with my undergraduate thesis, in which I developed an early detection system for tip burn using a CNN-based model. In that project, data annotation proved to be particularly difficult.
Okay, thank you for your question. Yes, I have experienced this kind of problem, so annotation. So it took a long time, a lot of effort. So maybe 5 years ago, so I annotated the targets by myself, so by hand. So, but now we developed the special so Python program to annotate automatically so with AI. So that's why so so it helps us do annotation for a short time. So there is a automation annotation service, but it's very expensive. And so if you can, so you develop autonomous annotation system by yourself. This is my answer.
Okay, thank you, Dr. Shimomoto. Okay, I'll go back to the on-site participants. If there are any questions, maybe you can raise your hand. Or maybe for the online participants, if you want to ask questions directly, you can use the raise hand button and I will allow you to ask question directly.
Okay. So I want to answer more.
Okay.
So previous question. So basically, so our system, So annotation. So the so if you reduce the number of the annotation, so number of the image for training. So if you should the so you should make effort to reduce the taking an image. It means the in our monitoring system. So for our monitoring system, we don't so training images are not so a lot of training images is not needed. So because our monitoring system can capture the clear images for AI. So to reduce the number of the annotation, you should come up with a method regarding the taking the image, especially taking the image, I think.
Okay, thank you for the answer added. Okay, if there are no more questions from the participants, I will end this session with Dr. Shimomoto. Okay, before I end this session, please allow me to highlight some important notes from the sessions. Okay, so from the lecture, Dr. Shimomoto shared the use of AI in agriculture in Japan, including using the deep machine learning, robots, and drones. This is to overcome the issues in the agriculture sector, like the labor shortage by decrease and aging of farmers. And Dr. Shimomoto also shared some cases in fruit monitoring systems, such as in tomatoes and paprika, where it uses deep learning, and also in strawberries as well, using drone to expose young leaves in strawberries. Also use of AI in maturing fruit count prediction. Also use robotic for pruning of tomato. Also other AI implementation in agriculture, including leaves removing robots for cucumbers, tomato harvesting robot, and also the promising of autonomous driven vehicle. Okay. Okay, once again, thank you, Dr. Shimomoto, for your time and insightful presentations. And also thank you for all the participants for the active participations. Okay, once again, please give a big applause to Dr. Shimomoto.
Thank you.
Okay, for Dr. Shimomoto, is there any final words from you to all of the participants, maybe?
Okay, thank you for having me today. And so I think there is so you all is a very talented, so excellent. So please use the AI for agriculture, and agriculture. So AI is just tool, and it become so running AI is become easy by year by year. So please try. Yeah, that's all. Thank you.
Okay, thank you very much, Dr. Shimomoto. I will return the session to the Master of Ceremony.
Okay, so thank you so much for Dr. Kota Shimomoto for the insights, and also Dr. Inasanati Pananwangi as our moderator. Before this session is over, we would like to have documentation with the speaker, moderator, and all of the participants. So for our online participants, if you are able to turn on the camera, please turn on the camera for a while, and the operator and the media team may take a screenshot. Okay, so please turn on your camera for the online participants, and we can count by 1, 2, 3. So thank you for turning on your camera for the documentation. And next we can move on to the certificate of appreciation. We will give a certificate of appreciation to Dr. Kota Shimomoto. The certificates will be given symbolized by our moderator.
Okay, thank you, MC. Okay, to express our gratitude to Dr. Kota Shimomoto, we would like to deliver an e-certificate of appreciation to Dr. Kota Shimomoto from the Dean of the Faculty of Agriculture, Universitas Gadjah Mada.
Thank you. Thank you a lot. So I'm very honored.
Okay, thank you very much.
Next, we will also give a certificate of appreciation to Dr. Inasanati Pandanwangi. The certificate will be given by the committee of the 7th summer course FTP UGM 2025. Okay, so with that, the session for today has finished. But we also would like to remind all participants to submit the post-test and group discussion assignment for today's activities. For the post-test, the deadline is 8 p.m. today. And for the integrated collaborative group work, please submit the assignment before 11:59 p.m. today. We also want to remind all the participants that